So let's take a little closer look here at Gauss's trick, in particular at the proof. Okay, so what I want to show you is that suppose that I start with the trick, and I'm going to define it like this. This is a property that is true of the number k, and I'm going to define that property as saying that 1 plus 2 plus 3 plus all the way up to k is actually equal to k times k plus 1 over 2, right? This is Gauss's trick. Now, I'm also going to kind of rewrite this a little bit. This is actually the sum from I equals 1 to k of I, right? And that is equal to k times k plus 1 over 2, right? This is just the notation that we use for sums, and you probably saw that in calculus, but if not, then it's just simply you take the I and you replace it by 1, and then by 2, then by 3, all the way up to k, and then you add all those terms, right? So if we have the sum of I squared, it would be 1 squared plus 2 squared plus 3 squared, and so on. Anyway, so P of 1 is basically something that says that the sum from I equals 1 to 1, that's just one term, of I, right, is equal to 1, which is equal to 1 times 1 plus 1 over 2. P of 2 is the property that the sum from I equals 1 to 2 of I, which is 1 plus 2, is equal to 2 times 2 plus 1 over 2. P of 3, the sum from I equals 1 to 3 of I, which is 1 plus 2 plus 3, is equal to 3 times 3 plus 1 over 2, and so on. Okay. Now, what we managed to show was that P of 1 is true. Okay, that was the first thing we did, right? You know, to do Gauss's trick, and then we showed that if P of 1 is true, then P of 2 has to be true. Okay, and from that we can conclude that P of 2 is true. Okay, we also showed that if P of 2 is true, then P of 3 must be true. And so, of course, that means that P of 3 is true. Okay? And we can do this as many times as we want. Like, for example, P of 100 implies P of 101. So P of 101 is true. And so on. Okay? So basically, the induction is a way of organizing these proofs. And we're going to organize it as follows. We'll show that P of 1 is true. Okay? And then we'll show that for all n, P of n implies P of n plus 1. Running out of room, aren't I? Now, the importance of that is that that actually captures all of these, right? So if I have P of n, then I can prove P of n plus 1 follows from that. So that gets me P of 1 gets P of 2, P of 2 gives me P of 3, P of 100 gives me P of 101, okay? And I get these with just one proof because I do for all n, right? So I have two obligations. I need to show P of 1, that's called the base case. And then I need to show that for all n, P of n implies P of n plus 1. That's known as the induction step. Okay, and this is the same as what we did originally, right? And this gets me all of the other ones. Okay, right? So the base case we have to prove both when we did kind of each step in the proof. But all of the other ones we simply get in one step because we do the for all, right? And this is what's known as induction, and in particular is known as mathematical induction. And we'll see different types of inductions, but this is kind of the basic form. So let's try to use it to prove Gauss's trick once and for all. Okay. So what we need to do is, first of all, we need to prove the base case. And the base case is when n is equal to 1, right? And what we have is that P of 1 is defined as the sum from I equals 1 to 1 of 1 is equal to 1 times 1 plus 1 over 2. Okay? And we'll just check that, right? So this is 1, And over here we have 2 divided by 2. Yes, that's true. Okay. I should actually prove it like this. The sum from I equals 1 to 1 of I is equal to 1, which is equal to 1 times 2 over 2, which is equal to 1 times 1 plus 1 over 2. Okay, that was just a sequence of equalities, but I took a shortcut in the first pass, but I'm sure you'll follow that. Okay, so let's do the induction step. And so this is a general case, and P of n then is the sum from I equals 1 to n of 1 plus 2, just I, and that's equal to 1 plus 2 plus 3 plus all the way up to n, and this is n times n plus 1 over 2. Okay, so what we need to show is that for all n, P of n implies P of n plus 1. Okay, so let's prove that. Okay, and the proof goes like this. The sum from I equals 1 to n plus 1 is equal to, of I rather, is equal to, and I'm going to do the boxing trick that I did at the beginning. I'm going to split that up into the sum from I equals 1 to n of I, and then I'm going to add n plus 1. Okay, so that's like when we did the original proofs, that we just put a box around the first part. The reason that we do that, okay, I might as well just call this definition of summation, right? I mean, that's really the property there. And here, this is equal to n times n plus 1 over 2 plus n plus 1, okay? And the reason that happens, that's just Gauss's trick. So I'll just call that P of n, right? And now, the rest of the proof is just algebra, okay? So we'll have n times n plus 1 plus 2 times n plus 1 over 2, and we'll factor out the n plus 1, and we're left with n plus 2. Oh, not 12, not 12. N plus 2 over 2, and I guess just to be pedantic, I'll write that as n plus 1 times n plus 1 plus 1 over 2. And so this is equal to that is exactly what we meant to show. Okay, so this is all just algebra. Okay, one last thing that I want to say. Right here, I used P of n. We called that the induction hypothesis. Okay, and when you do proofs by induction, okay, it is really important to be able to say what exactly is P of n. Okay, so be explicit, and then know exactly when you're using, right? So I'm trying to show P of n, and I can assume that. And when I use it, right, what I'm talking about, the assumption that I'm making is called the induction hypothesis. Okay, always be conscious and explicit when you use the induction hypothesis. Okay, so in an exam, for example, I'll ask you to actually tell me where is the induction hypothesis being used, and right here it is.